The ocean is a magnificent yet unpredictable environment. For most of us, a cruise ship evokes images of luxury, relaxation, and breathtaking views. But beneath the surface of calm waters lies a world of engineering marvels designed to keep these floating cities stable even in rough seas. Today, we'll dive deep into the science and engineering that ensures cruise ships remain safe, comfortable, and stable, no matter how turbulent the waters become. Every ship, from the smallest yacht to the largest cruise liner, relies on the principles of buoyancy and balance. Buoyancy is the upward force exerted by water that keeps the ship afloat. But staying afloat is only half the story. Staying upright is the real challenge. The key concept here is the center of gravity and the center of buoyancy. The center of gravity is the point where the ship's weight is concentrated, while the center of buoyancy is where the upward force acts. Engineers carefully design cruise ships so that the center of gravity remains low, keeping the ship from tipping even when waves push against it. Ship stability is also influenced by metacentric height, a measurement that describes how quickly a ship returns to an upright position after tilting. A properly calculated metacentric height is critical for both safety and comfort. Too high, and the ship may be stiff and uncomfortable. Too low, and it may become dangerously unstable. The hull is the backbone of any ship. Cruise ships feature wide, deep hulls with a specially designed shape that slices through waves while minimizing rolling and pitching. One critical element is the beam, the width of the ship. A wider beam increases stability by spreading weight over a larger area. Modern cruise ships often use a bulbous bow, a protruding bulb at the front of the hull that reduces drag and minimizes the pitching motion caused by waves. Additionally, the hull's shape below the waterline is carefully calculated using advanced computer simulations to ensure the vessel handles rough seas gracefully. Hull construction also incorporates materials and reinforcements that add strength without excessive weight. Engineers use high-tensile steel and advanced composites to create a hull that is both robust and flexible, allowing it to absorb the forces of large waves without compromising safety. Even the most stable hull cannot eliminate all motion in turbulent waters. This is where stabilizers come in. Modern cruise ships use large retractable fins on either side of the hull. These fins work like airplane wings in water. They generate lift to counteract the rolling motion caused by waves. When a ship begins to roll, the stabilizers adjust their angle automatically, smoothing the motion. Some ships even feature active stabilizers, which use real-time sensors and computer controls to react instantly to changing sea conditions. This technology dramatically reduces seasickness and keeps passengers comfortable. In addition to fins, some cruise ships employ gyroscopic stabilizers. These massive spinning flywheels create resistance to rolling through angular momentum. While less common, gyroscopic stabilizers are highly effective, particularly in mid-sized vessels and yachts. Another engineering solution for stability is the ballast system. Ballast tanks, located at the bottom of the ship, can be filled with water to adjust the ship's weight distribution. In rough seas, water can be pumped into specific tanks to lower the center of gravity, improving stability. Some cruise ships feature dynamic ballast systems, which adjust automatically based on real-time sensor data. These systems ensure that the ship remains balanced even during sudden shifts in cargo, fuel, or passenger load. By continuously monitoring and adjusting ballast, engineers can maintain optimal stability throughout the voyage. Cruise ships are essentially floating cities, and the distribution of weight inside is crucial for stability. Heavy machinery, engines, and fuel tanks are placed as low as possible to lower the center of gravity. Passenger areas, restaurants, and entertainment facilities are positioned higher, but always with careful consideration of balance. Designers also use computer modeling to simulate the effects of passenger movement, luggage, and onboard activities. Even minor shifts in mass can impact stability, so designers plan layouts to minimize potential imbalances. Modern cruise ships are equipped with advanced monitoring systems that track stability in real time. Gyroscopes, accelerometers, and motion sensors feed data into onboard computers, which can automatically adjust stabilizers, ballast tanks, and propulsion to counter waves. This integration of automation ensures that human error is minimized. Captains receive constant feedback and recommendations, allowing them to navigate rough seas with precision and confidence. In extreme conditions, automated systems can make split-second adjustments faster than any human crew could, reducing risk and maintaining passenger comfort. The way a ship moves through water also affects stability. Propulsion systems are designed not only for speed, but for smooth handling. Azimuth thrusters, for instance, allow precise steering while maintaining balance. When encountering large waves or strong winds, captains can adjust speed and heading to reduce rolling and pitching. Some advanced vessels also use dynamic positioning systems, which automatically maintain the ship's orientation and position even in rough seas. This technology is particularly useful near ports, shallow waters, or during rescue operations. To understand how these systems work together, we can look at real-world examples. The largest cruise ships in the world, carrying over 6,000 passengers, routinely navigate open oceans with waves exceeding 30 feet. Thanks to hull design, stabilizers, ballast systems, and advanced monitoring, passengers often barely notice the motion outside. Smaller expedition ships, designed for polar waters, use even more sophisticated stabilizers and reinforced hulls. These vessels must handle ice, strong currents, and extreme winds, making stability systems even more critical. Even with all these engineering marvels, safety protocols are essential. Cruise ships have strict operating limits, and captains can alter routes, reduce speed, or seek shelter when conditions exceed safe thresholds. Life-saving equipment, evacuation plans, and crew training are all part of ensuring passenger safety in extreme situations. Redundant systems are also a key design principle. If one stabilizer fails or a ballast pump malfunctions, backups are available to maintain stability until repairs can be made. This layered approach ensures that no single failure jeopardizes the ship's safety. The stability of cruise ships is a result of centuries of naval engineering, modern technology, and careful planning. From hull design and stabilizers to ballast systems and real-time monitoring, every aspect is optimized to keep the ship upright and passengers safe, even in the roughest seas. Next time you watch the waves from your cruise cabin, remember, beneath your feet lies a complex system of physics, engineering, and innovation, all working together to make your journey smooth and secure. The ocean may be unpredictable, but cruise ships are designed to face it with confidence.